Hey guys, this pebble that I'm holding in my hands is lithium hydride. This is the lightest ionic compound. Ideally, lithium hydride appears white, but exposure to light causes it to turn gray-blue due to the formation of a solid colloidal solution of elemental lithium within the compound. Thorough storage in air leads to a formation of carbonate, resulting in lithium hydride acquiring an orange tint. Lithium hydride reacts very actively with water, producing a huge amount of hydrogen. This compound burns emitting a red flame. Lithium hydride has one unique property, which will be discussed in this video. The fact is that if it's melted, it will acquire such strong reducing properties that it can convert liquid inorganic chlorides into higher hydrides of these elements. When melting lithium hydride, at least a minimal inert atmosphere must be created in the test tube. For this purpose, only argon or more expensive inert gases are suitable, because in air, lithium hydride can easily ignite, and with nitrogen it will quickly react to form lithium nitride and ammonia. Demonstrating this experiment is not easy. It will require expensive quartz test tubes because the melting point of lithium hydride is almost 700 degrees Celsius. So, in the first experiment, I'll add phosphorus trichloride to the molten lithium hydride. In slow motion, you can clearly see how the phosphine formed in the reaction spontaneously ignites in air. For the next experiment, I'll have to break this ampule containing 200 ml of silicon tetrachloride. By the way, I found this reaction in one of the articles. It suggests dissolving lithium hydride in lithium chloride and potassium chloride to reduce the melting point. So, let's finally add silicon tetrachloride to the molten lithium hydride. It's obvious that in this reaction only silane burns this way, with the formation of white smoke consisting of small particles of white silicon dioxide. It's also called white soot. Although the boron halides, only boron tribromide is liquid at room temperature. This is what I'll use to produce Diborane, which is self-igniting in air. Such a meteor shower in this reaction is most likely associated with the incomplete melting of lithium hydride. This time I didn't melt it a little until it became homogeneous, and therefore the resulting gas captured solid particles of lithium hydride. An equally powerful meteor shower occurred when I added this yellow oily liquid, antimony pentachloride, to the molten lithium hydride. Ideally, freshly distilled antimony pentachloride is a colorless liquid, but during storage it turns yellow due to the admixture of chlorine. In the following reaction, hoping to obtain titanium tetrahydride, I used titanium tetrachloride. It's strange, in this reaction we didn't see anything other than purple smoke corresponding to titanium trichloride. Is it really possible that titanium tetrahydride is not formed in this reaction? In fact, it's formed, it just doesn't always ignite in air, but it does so easily when in contact with ozone. I repeated the experiment, only this time I attached a glass tube above the test tube through which I would supply ozone, or rather ozonated oxygen. Let's see what happens in this case. Most likely these falling white flakes are mostly titanium dioxide, formed as a result of a combustion of titanium tetrahydride. Yes, in slow motion you can clearly see how in the absence of an open flame, and only at a point of contact with ozone we observe ignition. In this reaction, this can only indicate the formation of titanium tetrahydride. I repeated the same experiment using tin tetrachloride. First, I added it without using ozone. The result was a weak flame, it didn't burn for long. Then I added ozonated oxygen to the experiment. Regarding this reaction, I cannot say anything definite whether Stannane is formed here, or whether it's the combustion of hydrogen mixed with tin ions in the oxidation state 2+, which is capable of coloring the flame pink, but not violet as here. Write your comments what you think about this reaction, whether there is Stannane here or not. So guys, I'm sure you like these reactions, which would have been impossible without the help of my patrons. Join these wonderful people if you have a desire and opportunity to help me create new chemical videos. Thanks for watching, see you in the next video.